Welcome to Unit 12, which is Introduction to Multi-Level Modeling, which is going to be your last unit for Psych 653, actually. Woo! So just to get started, I wanted to start off by saying multi-level modeling is a huge, complex topic, and we're really only going to be scratching the surface with what we're going to be doing here. Oh, Emma, you're going to have to switch slides.
Before we get started, just want to do a quick shout out to Dr. Kim Henry in our department. A lot of these materials are from her. She used these to teach our class when Neil and I took it, and we figured we don't need to reinvent the wheel with high quality stuff already. All right, so we're going to do a quick overview of the concepts of multi-level modeling. This is going to be pretty similar to what we did previously with nested data or using the Elmer package for longitudinal data. Multi-level data occurs when we have individuals that are nested within different groups. So for example, you might have individuals who are nested within a certain organization, different levels of hierarchy.
All right, so the first things that we're going to do is load up all of our packages. We'll be using the Tidyverse package, the LME4 package, which you used with nested data and longitudinal data before, the Psych package for describing, and then a new package called the Mumin package, which is essentially to get our pseudo R-squared values, which we'll be obtaining later. So you'll have to probably install that package. Okay. And today we'll be using the Teams data. Which I don't think we've actually used in the past before. So this data set includes 500 female high school students who participated in a summer science program, and essentially they're categorized into risk indexes from, I believe, 0 to 5 was the risk index, based on how they were previously doing it academically before. So higher risk indicates more risk of not doing good on some sort of task, lower risk indicates lower risk of doing good on some sort of task. So these students were randomly assigned to teams of 5 and given the summer program to see how they did at the end of this program on a certain kind of task.
And the teams were either assigned to a control or a treatment condition. So taking a look at the structure of the data, we have some level 1 variables and some level 2 variables. The level 1 variables, remember that's the individual level. That's going to be each student's ID number, the risk index, that'll be the variable that we look at in these analyses. And we also had belief in communal affordances of a STEM career, and the final exam score is also at the individual level. The level 2 variables, the group level, essentially, this is going to be the team ID and then the treatment condition that the team was assigned to. So you can kind of picture here, all of the kids are nested within a certain team, hence the hierarchical structure. First thing we'll do before getting into multi-level modeling is we are going to factor our variables. This should look familiar. Team ID is going to be a categorical variable. So here we're just using mutate to tell R to read it as a factor.
And then the next thing we're going to do is we're going to get something called the mean of means. And this is essentially the mean of our outcome variable across all groups. You can go ahead and just copy down this code, but first we're going to be grouping them. Then we'll be summarizing the team's means and then getting a mean of all of the means overall. But just so you know, we use this value for some really important aspects in graphing and to kind of illustrate some very important things about multi-level modeling. So the mean of means is actually going to come up quite often here. So here our mean of means is 73.216, and we'll continuously be seeing this come up in our model output as well.
So before we get started with running our models, we first wanted to visualize our data to just take a look at how does the final score, our outcome variable, vary across the teams. Are all the teams showing a pretty similar pattern, or are there some differences? These plots that we're showing are optional. If you want to get some ggplot practice, we encourage you to try it out, or at least copy and text this code to have it for a later time. But you'll see here the mean of means value. We did include it for our y-intercept. And taking a look at that plot here, that dashed value along the top, that is our mean of means that we saved. That is the value that we calculated a couple slides ago. And what we're looking at here, we've got team ID along the bottom. We have 100 teams, and then we have the final score, and then we have box plots along it. And what we can see is that the teams seem to vary quite a lot in their means. A lot of spread to the data here. Anything to add, Neil?
Yeah, beyond the means, as you can see, some teams have a lot of variability, other teams have very little variability, which means their scores are very close to each other, or sometimes their scores are very far apart from each other. So really, there's variation across just the means, both within team and between teams as well. Yeah, so what we're going to be using here is the Elmer function, in which as stated before, we used those before, this function as well before. So the Elmer function is a function used to specify for multi-level models. It starts off running very similar to the LM package, in which you use your Elmer function, you indicate the outcome variable to the left of the tilde, and then to the right of the tilde would be any fixed effects that you have. In this condition here, we only have an intercept. We're actually not going to be using any fixed effects. However, we will have a random intercept of team ID here, which we indicate by putting in parentheses a 1, and then we use a straight line, which is called a pipe, and then your random effect intercept, which here is a grouping variable, which is our team ID. Most oftentimes, or I think actually all the times, your grouping variable will be your random effect. Here. Anything else? Oh, cool. Okay, and I can go ahead and talk about fixed and random effects as well. So remember, we have the unfortunate thing about a lot of our psychology statistics is that fixed and random effects take on different meanings. So I want to make sure that it's clear what we mean by fixed and random effects in terms of multi-level modeling. So a fixed effect is something that does not vary over subjects or groups. So the average value or the average intercept, that's when we're going to be talking about a fixed effect. So as Gemma stated in here, so as an example is, what is the estimate of the effect across all groups? That's the question you're asking with fixed effects. Whereas random effects, they might vary across subjects or groups. So whenever I'm saying how much of the intercepts or slopes vary across groups and between subjects, that's when we're talking about random effects. So really what you'll be asking yourself is, how much does the estimate for the effect vary across the groups for random effects? And really, random effects, you're looking at the variation between groups. Fixed effects, it's the average of the group.
And most models that we've done so far would account for fixed effects. We're not grouping participants by grouping level. It's just what would the average effect be. And here we're able to break it down more by group. There are a couple different effect sizes that we'll use in multi-level modeling that we haven't come across before. The first one is intra-class correlation, abbreviated as ICC. And this is going to be the proportion of variance in a level 1 variable, basically an individual level outcome, that's accounted for by a level 2 variable. For example, how much variance in Y is explained by the groups that the participants were in. Another interpretation would be the average correlation of a level 1 variable between two individuals in the same level 2 group. And so amidst different groups, how similar are all of the participants in each group? Some of the general rules of thumb, an ICC over 0.2 or 20% of variance explained generally indicates a meaningful effect. But if you have a value of more than 5% or 0.05, that's normally worth further investigation. We calculate this, we'll show you the formula later, but essentially you're dividing the random effect variance by the total variance. So you're really dividing, how much is the grouping variable, the amount that varies by groups, how much of variance is explained by that. The other effect size that we'll look at are pseudo R-squared values. Now these are not completely equivalent to our normal R-squared from an OLS regression. And if you were to run equivalent OLS regressions on the data, you wouldn't get the same values. They're kind of similar to the ICC. The marginal R-squared is the amount of variance explained in Y just by the fixed effects in the model. The conditional R squared is the amount of variance explained in Y by the fixed and random effects. And the difference between these can also give you a sense of how much the random effects are contributing.
Okay, so we're going to start with our first model in which we only incorporate a random intercept only. So as you can see with my pointer, we're using the Elmer package again. Our outcome here is score. We use the tilde, and then we use a 1 as a placeholder for our intercept, and just indicating that we just want one fixed intercept. Then we use an addition sign, and then in parentheses enclosed, we're saying that we're going to use a random intercept of team ID.f. So we want to see how much do teams vary from the grand mean of all of in terms of score. So and then what you'll see is we get two sets of coefficients. We get random effect coefficients and fixed effects coefficients. I'm going to start off by looking at the fixed effects coefficient to notice that we have our mean of means appear as our fixed effects coefficient when there's only on random intercept only without the presence of any other fixed effects. So if we go ahead and go to the next slide, we can see that still we remain with our intercept of 73.216, which is the mean of means. And additionally, we can talk about our random intercept, which is the average, which is how much on average each team varies from the grand mean. So in this case, on average, the mean of each team varies from the grand mean by 8.979 standard deviations, as is highlighted in blue here. Additionally, the fixed intercept, as I mentioned before, in the absence of any fixed effects, this intercept represents the mean of means of our outcome variable. So on average, all the teams have a score of 73.216, and they vary by an average of 8.979 deviations.
That's a pretty big deviation from the mean.
Yeah, that's a really large deviation, which makes it seem like this might be something worth looking into.
Mm-hmm. All right, so we went ahead and we calculated the effect sizes for this model. The first over on the left is the interclass correlation. And then we have the variance of the random effects divided by the total variance, and we calculated that out here. We got a value of 0.53, which indicates that 53% of the variance in final test scores could be attributed to differences in the teams. That's a pretty large amount of variance in performance just based on the teams that people were randomly assigned to. Over on the right, the pseudo R squared. If you remember, there were two different types of pseudo R squared. The marginal is just about the fixed effects. Here we didn't have fixed effects, so that's just a blank NA. Then we have our conditional pseudo R squared, which is saying that 53% of the variance can be explained by the model's fixed and random effects. Here, this is the same as interclass correlation because we only had a random intercept.
Great. And then now we're going to run another model, in which case now we have a random intercept but a fixed slope. So what that means is that we're allowing our intercept to vary, but we're not allowing our slopes to vary in any way. So we've added risk as a fixed level 1 predictor, and you'll notice as I kind of pointed out with my mouse that we put risk as 1 plus risk on the left side of those parentheses there to indicate that this is a fixed effect. So when we enter in our code, and what we get is a random intercept, a fixed intercept, and a fixed slope. So on our random intercept, highlighted in blue on the left side, is saying that on average, our team intercepts vary by 9.128 standard deviations. While our fixed intercept, and you'll notice that our fixed intercept and our fixed slope is going to remain the same for the rest of the models because they're not quite changing based on things, but our fixed intercept is saying that the average intercept while incorporating risk is 77.868. So on average, while incorporating risk, teams are scoring 77.868 on their score. And the fixed slope is indicating that on average, team scores decrease by a rate of 2.326 units for a 1 unit increase in risk. So keep that in mind. And what we're going to do is we're actually going to spend the next couple slides visualizing how this looks as well.
Mm-hmm. So this is, again, code from Kim Henry. I'm not going to spend too much time going through the weeds of it. This is available to you, and please ask us if you have any questions about the coding. But what this code gives us is this plot here, which is essentially plotting the model we just ran. So as Neil was talking about, the red line is the slope of the fixed effect. This is going to be the average amount of change across risk quintiles in final score across all of the teams. Each individual black line here is an individual team. And so here, the slope in this model is fixed. So all of the slopes are the same, but we are seeing how the different teams are varying. Anything to add, Neil?
No, that's just simply looking at the variation on the intercepts and seeing how much these teams vary on their starting score when the risk is 0.
Okay, let's take this slide again. Yeah. We went through and we calculated the ICC and the pseudo R-squared. Here, adding the fixed slope means that we were explaining essentially more of the variance in final test scores could be attributed to differences between teams when we have risk in the model. The marginal R-squared, we have one now because we do have fixed effects. So 7% of the variance can be explained by fixed effects, which was risk in this case. 62% of the variance could be explained by the model's fixed and random effects. So we're counting for risk and for team ID here.
All right, and now we have a third model. In this case, we're going to be having a random slope, so allowing the slopes to vary. However, having a fixed intercept, so not allowing the intercept to vary in any way. And I'm actually going to go to the next slide so that we can talk about it. So the way that we indicate a fixed slope, a fixed intercept, is by indicating that through this, where we had a 1 before, we indicate it on a 0 on the first part of that parentheses. And that's saying, okay, we want to have our random intercept in there, but we're going to keep it fixed. So this means that no one can vary on risk quintile 0, whenever risk is 0 in this case. So we plugged in a 0, and we got a random slope, a fixed intercept, and a fixed slope. Notice how we did not get a random intercept at all because simply we kept it fixed. So what we're saying is that on average, our slopes are varying by a standard of 3.364 standard deviations as highlighted in purple here. And then our fixed intercept and fixed slope are actually the same as they were before, in which we're saying that on average, when we're incorporating risk, our intercept is at 77.868, and our fixed slope is on average, team scores decrease at a rate of 2.326 units for every 1 unit increase in risk, keeping in mind that the fixed intercept and fixed slope are the average. And then for the next slides, we're going to go ahead and visualize how this looks as well. So, sorry, I got this. So keeping in mind, we're not going to kind of go into the weeds on this one as well, but this is an optional way so that we can plot what the next graph is going to make. So as you can see, we plotted the fixed intercept. As you notice that the intercept is exactly the same for all of these. However, the slopes have changed drastically. So every team has their own individual slope, but they all start at the same risk quintile score at 0 for the intercepts. So it's a funky looking graph, but it's a graph that is graphing exactly what we mapped out before.
Mm-hmm. Yeah, exactly. When we hold the intercept constant, but let the slopes vary, this is what the data looks like. Mm-hmm. Same interpretations of these effect sizes here. I'll be our effect size person today. We calculated our ICC of 0.13. This is, you'll notice, lower than the last couple of slides. 13% of the variance in the final test scores could be attributed to differences in the groups. Over here in our pseudo R-squared, again, we had a 7% for our marginal R-squared and then 52% of the variance for our conditional R-squared by both the fixed and random effects.
You want me to take this one, or yeah? Okay, I can take this one again. Okay, so and then I'll actually do the effects sizes this time too, Kachema. Okay, so let's talk about Model 4, in which we do all random effects here. So really, this is just like all of your other ones, except now everything is free to vary as much as once. So we have both fixed effects and random effects in this one. And I'm going to go ahead and ask you to go to the next slide.
Mhm.
So now you'll notice we have a random intercept, a random slope, a fixed intercept, and a fixed slope.
Mhm.
So what are we saying with the random intercept? So now in the presence of a random slope and the fixed intercept and fixed slope, we're saying on average team intercepts vary by 8.922 standard deviations as is highlighted in blue. Um, and then on average, our team slopes vary by 2.665 standard deviations. And then our fixed intercept and our fixed slope remain exactly the same. So we're saying that on average, people are scoring at 77.868 while incorporating risk. And on average, team scores decrease at a rate of 2.326 units for every 1 unit increase in risk.
Mhm. And so essentially what we'll show in the visualizations, in a lot of ways, this is the most realistic representation of the data in that we're actually going to allow the data to map out based on how all the different teams did. Same deal with the code. Please reach out if you have any questions about it. And here what we're looking at is, again, we plotted our mean, our fixed effect with the intercept and the fixed slope averaged across all of the teams. And all of the black lines here really represent what would really be estimated to be the intercept and the slope for each team when they're not specified to be fixed to the mean. Yeah, so this is a more accurate representation of how all the teams actually did.
Okay, and I'll be the effect size person this time. So when we calculate our ICC, we incorporate the random intercept and the random slope into our equation this time. We get an ICC of 0.68, and we're saying that 68% of the variance in final test scores can be attributed to the difference between teams. That's a pretty large amount. That's a lot of variance that we can attribute to that. Which really is leaving evidence saying, yeah, teams seem to matter in our models. Additionally, we can calculate our pseudo R-squared variance. So we start with the R-squared marginal, in which we say 7% of the variance in scores can be explained by the model's fixed effects. And then we can go ahead and talk about our conditional R-squared value, pseudo R-squared value, in which now we're saying 73% of the variance in scores can be explained by the model's fixed and random effects.
So the next step here, this is going to look really similar to what we've done in hierarchical regression. And multi-level modeling, the term is a log likelihood test or log likelihood ratio test. And here we're going to go through and we're going to do pairwise comparisons. We're going to compare each of the 4 models that we built. We're going to compare the first 3 to the final model that had all the random effects. And the main takeaway from this is that if our chi-square value exceeds the critical value of the chi-square, we can say that that second model accounted for a significantly greater amount of variance than y, or significantly improved model fit. So again, we're looking for a significant p-value here. So first of all, we compared the random intercept only to the all-random model. This significantly improved our model fit. We did the same thing with the second model, the one that had the random intercept fixed slope versus the all random. Again, the all random effects model significantly improved model fit. And we saw the same thing when we compared the third model, the fixed intercept random slope versus the all random. And essentially what we're saying, and kind of what we saw in those plots, is that the all random model really explains more of what's happening in the data. It allows us to really account for these differences in teams that were pretty substantial. So it makes sense conceptually and from visualizing the data that the all random model is going to be the way to go for modeling our data most accurately.
And that concludes the show.
That
All right.
our lab for the semester.
Yeah. Thank you, everybody, for coming and listening in on our presentations. I know it was a little weird at the end of the semester there, but we really appreciated everyone in the class and really enjoyed teaching everyone.
Yeah, I agree. Thank you, Neil, for saying that. I echo that.
Yes. All right. Thanks, everybody. Bye.